Assalamualaikum warahmatullahi wabarakatuh. We're from Group 6 and today we are going to present about Stokes Theorem. Before that, let me introduce our team members, starting with me, Nur Salmi, followed by Nur Shamila, Alia Inshira, Julia Batrisha, and Nur Atira.
We will begin by briefly introducing the definition of vector calculus. Vector calculus is a branch of mathematics that extends the concepts of single variable and multivariable calculus to vector valued functions and vector field. It involves operations like the gradient, divergence, and curl, and is used to understand real-world phenomena such as fluid flow, electromagnetisms, and mechanics. Now, let's focus on Stokes' theorem, one of the key theorems in vector calculus. Stokes' theorem connects two types of integrals, the line integral of a vector field along a closed curve and the surface integral of the curl of the field over the surface bounded by the curve. The theorem was named after Sir George Stokes, who introduced it in the Cambridge exam in 1854. It was based on earlier work by William Thomson and Carl Friedrich Gauss. The theorem can be written as the closed line integral of vector f dot dr equals the double surface integral over S of the curl of vector f dot n ds, where C is the closed boundary curve, S is the surface bounded by C, F is a vector field, and N is the unit normal vector to the surface. For Stokes' theorem to apply, certain conditions must be met, which is the vector field must have continuous partial derivative, the surface must be piecewise smooth and orientable, the boundary curve must be closed and positively oriented, which is counterclockwise when viewed from above. In short, Stokes' theorem provides a powerful way to relate the behavior of a vector field over a surface to its behavior along the boundary of that surface.
Now, let's move forward to the problem statement. So here's the question for our first problem statement that we're going to discuss in this presentation. Now, I'm going to explain how to evaluate a line integral using Stokes' theorem with a step-by-step manual calculation. So we start by applying Stokes' theorem, which allows us to convert a line integral around a closed curve into a surface integral over the curl of the vector field. Next, we compute the curl of the given vector field. Using the determinant method, we arrange the unit vectors I, j, and k and the partial derivative with respect to x, y, and z, along with the components of the vector field, which are negative y, x, and z squared. After solving, we get 0 in the I and j directions and 2 in the k direction. So the curl of the f is the constant vector 0, 0, and 2. Now, since the surface lies in the plane where z equals to 0 and the curve is oriented counterclockwise, the surface normal vector points straight up in the positive z direction. That means our normal vector is just the unit vector k. Taking the dot product of the curl and the normal vector gives us 2, which simplifies the surface integral to just integrating 2 over the circular region bounded by the curve. To solve this, we switch to polar coordinates. The double integral becomes the integral of 2r, where r range from 0 to 1 and theta from 0 to 2 pi. Solving the inner integral gives 1, and then integrating with respect to theta gives us 2 pi. So the final value of the original line integral is 2 pi, which is approximately 6.2831.
So, for the maple comments for question 1, first, use plot 3D to draw the upper hemisphere of the unit sphere and space curve to plot the boundary circle in green at the base. This visual helps us understand the surface S and its boundary C, as required in Stokes' theorem. Next, define the vector field as vector fxyz equal to negative y x z squared. Then calculate the curl using the curl comment in maple, and the result is curl f equal to 2z. That means the curl is pointing in the z direction and it's constant across the whole surface. After that, convert the curl f and you will get 0, 0, 2. To apply the surface integral, we use spherical coordinates to represent the surface part equal to sin phi times cos theta, sin phi times sin theta, and cos phi. This parameterization covers the upper hemisphere where range phi from 0 to pi over 2 and range theta from 0 to 2 pi. Next, calculate the partial derivative of r, then use the cross product to get the surface normal vector n. Then, compute the dot product of the curl and normal, giving the integrand 2 sin phi cos phi. Finally, set up the double integrand over phi and theta using the integrand. Maple gives the result as 2 pi and the decimal value is approximately 6.28318.
Next, this is the second question, which is question 2. Now, I will present the manual solution for question 2. Stokes' theorem relates the line integral to the surface integral of curl f and ds. Start by finding the curl of f, which gives 0, 1, negative 1. From the surface z is equal to x squared y, I take the gradient and adjust for orientation to get the normal vector negative 2xy, negative x squared 1. Substitute into the surface integral 0, 1, negative 1 dot negative 2xy, negative x squared 1, and I got negative x squared, negative 1. I factor out the minus sign, so it becomes negative in bracket x squared plus 1. Since the region is a circle when viewed from above, when I switch to the polar coordinates, dA becomes r dr d theta, x is equal to r cos theta, so x squared is equal to r squared cos squared theta. The integrand becomes r cubed cos squared theta plus r. Limits are r from 0 to 2 and theta from 0 to 2 pi. After integrating r and simplifying, I got negative limit 0 to 2 pi for cos squared theta plus 2 d theta. I factor out the 4 and use the identity cos squared theta is equal to 1 plus cos 2 theta over 2. It simplifies to negative 2 limit 0 to 2 pi cos 2 theta plus 1 d theta plus 4 pi. After integration, I got 2 pi, so the total is 4 pi plus 4 pi is equal to 8 pi. With the minus sign, final answer is negative 8 pi, or approximately negative 25.1327. Even though the curve is counterclockwise, the result is negative due to the direction of the dot product. That's all for the manual calculation of question 2.
We begin the mapper session by clearing all previous data using the restart command. Then we load two essential packages, vector calculus and plots. The vector calculus package is used for operation involving vector fields such as curl and dot products, while the plots package allows us to create 2D and 3D visualization. The next part involves creating a 3D plot of a parabolic surface using the plot 3D command. The equation of the parabola is written in cylindrical coordinates as r square cos square theta minus r sine theta. The plot is customized with a pink surface color and transparency to allow better visualization of the other objects. We also plot a circle in the xy plane using the space curve command. The parametric equation for the circle is x equals to 2 cos t, y equals to 2 sin t, and it is colored cyan with a thicker line for emphasis. Both the parabola and the circle are combined using the display command to provide a complete 3D view of the system. Before proceeding with vector calculus operations, we need to specify the coordinate system. We use the set coordinates command to select the Cartesian coordinate system, which is required for calculating the derivative and curls correctly in the upcoming steps. A vector field f, x, y, z is then defined using the vector field command with the components y, 0, and negative x. This vector field represents a rotational flow that we will analyze further. When displayed, it shows the vector f, y, 0, negative x. We calculate the curl of the vector field f using the curl command. The curl measures the rotational tendency of the vector field. The result is A equals to 0, 2, 0. This indicates that the rotational tendency is constant in the y direction. Next, we define a scalar function, z equals to x squared y. We compute its partial derivatives with respect to x and y. The partial derivative of z with respect to x is 2xy. The partial derivative of z with respect to y is x squared. This step is useful to understand gradient components and changes in the scalar field. A new vector field is then introduced in polar coordinates using the vector field command. The components of this field are negative r squared cos theta and 1. This vector field will later be used in the dot product and surface integral calculations. We calculate the dot product of the curl vector A and the new vector field n. The dot product result is A dot n equals to negative x squared minus 1. This result will be used as the integrand in the next step. We set up a double integral in polar coordinates over a circular region with a radius of 2. The integrand is the expression from the previous dot product. This double integral represents a surface integral that sums the contribution of the vector field over the circular region. Lastly, the double integral is evaluated numerically using the eval command, giving the result W approximately equals to negative 25.13274,123. This is the final answer, representing the total flux.